Hello and welcome to EE333. I'm your instructor, Gregory Myers. In this video, we're going to start a new demo project that's going to focus on 2D or two-dimensional geometry. We're going to call this our Shape2D demo, and we're going to start by creating a new Java application called Shape2DDemo. And the driver or the class that has a main in it will be called Shape2D driver. And we will once again put it in our EE333 namespace or package. And the idea here is that this is going to be a compatriot or a parallel project to our inheritance demo so that you can see several different ways to utilize inheritance as well as some of the access modifiers like public, private, protected, and we'll also get an opportunity to look at an abstract class. So this video assumes that you have gotten started with your inheritance demo and understand the idea of inheriting from a parent class or extending a subclass from a parent class. The first thing that I want to do is I want to take a look at a draw.io diagram that I've created, or a UML diagram. I have not filled in all of the details here, but essentially what we want to do is we want to create a class hierarchy that leverages a two-dimensional base class or Shape2D base class. And as you go along through this example, we're going to add additional subclasses, and you're also going to realize that there is more than one way that we could go about doing this. So first, let me give you the backstory. The idea here is that we would like to be able to create a set of classes that allow for us to perhaps create a graphical user interface where we can, for instance, display some geometry, maybe an geometry like an isosceles triangle or a square, and perhaps be able to rotate the square so that you can visualize it. And as you rotate it, the region that is bounded by that particular shape is going to change. So you want to think of it sort of like a circumscribed region, or the area, then the smallest area that can, or the smallest rectangle that then can bound your two-dimensional shape. This is useful for a number of applications. In addition, what we're going to do is we're going to utilize these subclasses to be able to calculate certain properties of each of our two-dimensional shape objects. So for instance, you might want to be able to calculate the area or the perimeter of one of your shapes. But the idea here is that we want to focus more on the inheritance and looking at where we can identify unique features of a subclass and perhaps further refine the parent class. So for instance, there's two ways to look at this particular portion of the diagram. You'll see that I have an ellipse that inherits from a Shape2D parent class, and then a circle that inherits from an ellipse. Now, you could argue that the circle could inherit from the Shape2D parent class, and then the ellipse would extend the circle, because this ellipse is essentially a more generic circle because it has two dimensions, a minor axis and a major axis, where the circle has essentially just one major axis, in other words, the diameter. But effectively, what we can do here is we can flip this around and say that the circle is a more specific example of an ellipse, meaning that we can have perhaps different equations that can be used to calculate the properties, simplification in some cases, or we can also discover new properties or specific properties to one of our subclasses that does not exist in our parent class. Once again, this project is going to be sort of a work in progress, and we're going to add new subclasses and fields and methods as we go along. Same down at the bottom, where you notice that we have the square and the rectangle, the square extending the rectangle, and the isosceles triangle extending the equilateral triangle. In this particular video, what we're going to do is we're going to focus on setting up the project and go ahead and get these first classes stubbed in. The one thing that you'll note is the use of italics on some of the class names, particularly the Shape2D and the irregular Polygon. We will use this to indicate that these classes are abstract classes, which means there can be no instance of that class being initialized. And particularly, we also want to include in that list the regular Polygon. What do I mean by that? Well, at least for right now, we won't be able to create an instance of an irregular Polygon because we don't have the means by which yet to properly describe an irregular polygon. Instead, what we want to do is we want to only rely on the concrete implementations of a square and rectangle with respect to a regular polygon. In other words, we'll focus on the implementations for the rectangle where we can identify the short and the long side or the length and the width, whichever way we would like to go about doing it. With the regular polygon, we can then revisit whether or not we want to start including the ability to import or create constructors for that geometry. However, initially, these three classes are going to be concrete, meaning that there can be no instance of these classes created by themselves. So let's get started and see how this works. What I would encourage you to do is to obtain a copy of this Shape2DDemo.draw.io. Don't be afraid to necessarily change it and make your own additions to it, but we're going to start with this base project and we're going to refine it from there. So to begin with, you'll notice that I already have my project set up here. We have our Shape2D demo and our Shape2D driver. The first thing that I want to do is I want to go ahead and create a new Java class. In this case, I'm going to call it Shape2D, and I'm going to make it part of my EE333 package. We could have just as easily included it in our Shape2D driver, but I would like to get into the habit of separating the driver from the class structure that we are going to make here, or what we're going to develop. The idea being is that you can then reuse this Java file then in other projects separate from the driver. The driver is just a means by which to test what we've done. Now, what we want to do is we want to remember what our draw.io diagram looked like, and occasionally we'll switch back to it. But the first thing that we want to do is we want to identify those abstract classes. And we said that our Shape2D was going to be an abstract class, meaning that there was going to be no constructor associated with this class, meaning that you couldn't just create a Shape2D. You could sort of think of that as being too vague. Now, at this point, what you'd like to do is you'd like to start identifying some private properties or some fields associated with a two-dimensional shape then that we can carry on through to our other classes. And I'll get us started with this. Once again, this project is going to evolve, and we're going to add fields and methods as we see fit. But at the very least, what you can start with is a private int n, which is going to indicate the number of sides. And in this case, what we're going to do is for anything like a circle or an ellipse, we are going to assume that rather than having an infinite, we're going to define it rather, instead of having an infinite number of sides, what we're going to do is we're simply going to say that a circle has sides n equal to 0 sides. And you'll see that really what this particular variable does is it helps us just identify which type of shape we have. And then from there, we can utilize some additional formulas, for instance. And you'll see as we go along what I mean by that. The next private variable that we want to have is going to be a double, and it's going to help us define the region that encompasses that shape, So essentially what you want to do, if we think of the circle for just a second, imagine putting a box around the circle. And the idea is that that region then would be what we would utilize to bound our 2D shape. So we'll start off, we have a region length and a region width. And then the last, at least in the beginning, the last field that we want to include here is going to be the orientation of the two-dimensional shape. So in this case, we're going to have a private double of orientation, and that just simply means how the shape, the 2D shape, is oriented within that bounding region. And the reason why we need that is because that will help us determine then the bounding region that is going to be used to define that shape. In other words, the size of the square or rectangle that will go around our two-dimensional shape. Now, conversely, you've probably seen in certain applications that if you were to rotate something, that essentially as the major axis becomes too long for the width or for the length of the bounding region, that essentially it would shrink our two-dimensional shape. We can also look into how you would calculate that. But for right now, what we're going to do is we're going to assume that we are going to change the region that bounds the shape to the object as we change the orientation. Now, what we'd like to do is we'd like to take a look at some of the constructors that we ultimately will need for the subclasses. And we will start with the public abstract Shape2D, but let's go ahead and flush out our entire subclass structure before we go any further. So as you recall from the diagram, we had an abstract class that we referred to then as an irregular polygon. And so take just a second to go back over to your draw.io and borrow the class names here. In this case, the irregular polygon. And specifically, we want this irregular polygon to extend our EE333.shape2D. Continuing with that, we said that we want to have our regular polygon extend from our irregular polygon. So once again, the extends EE333.irregular polygon. Continuing down our left branch of our UML diagram, we said that an ellipse was going to be a concrete class. In other words, it was actually going to have implementations associated with it. And it was also going to inherit from our Shape2D. So we can go ahead and create that. Doesn't really matter in the order that you do this. So the class Ellipse will extend our EE333.shape2D. And then likewise, our circle is going to extend our EE333.ellipse. And then the right side of the UML diagram, or the bottom rather, is used to continue to extend out the regular polygon. And here we start with the concrete classes for our rectangle. So we have a class rectangle that extends our regular polygon, or EE333.regular polygon. And we also have a class square that extends our EE333 dot rectangle. Now, the last two classes we'll go ahead and stub in, but we aren't going to get a chance to work with them in this video. We're going to have a equilateral triangle. And this, once again, is going to extend your EE333 regular polygon. And then lastly, you're going to have a isosceles that's going to, isosceles triangle rather, that's going to extend your EE333 equilateral triangle. And once again, we're going to come back to these. We may actually make some changes in our structure as we see fit, but we're going to focus sort of on the simpler shapes first. But the idea here is that we have a mix now of abstract and concrete classes, and they all inherit from our Shape2D, and our Shape2D has 4 private fields associated with it. And we're going to see then how we can extend each one of these subclasses. So the first thing that we want to do is we want to identify then what sort of getters and setters we wish to have. And so to begin with, let's focus on these 4 private fields. And we'll start off with the ability to get the n, or the number of sides. We have to ask ourselves, do we want to set the number of sides after the object is constructed? The argument should probably be no, because we don't want to inadvertently change a circle into a square or a circle into a rectangle by changing the n associated with it and ultimately messing up your calculations. We want to do that intentionally, not accidentally. So in other words, we may find ourselves doing that in another method, but we wouldn't necessarily want to have a public getter or a public setter for this. So instead, what we want to do is we want to focus on a public way to retrieve the number of sides. Likewise, we want to have a public way to retrieve the orientation. We can decide then how we want to set the orientation, because at this point, the Shape2D is too vague to know much about how to change its own region. So in other words, what we want to do is we want to have the ability to change the region or set the region. However, though, the orientation can be utilized then to determine what the region will be, but we will need to do that in the subclasses. For instance, if you rotate a circle, you don't have a change in region. However, if you rotate a rectangle or a square, you would. And so the question you want to ask yourself is, who knows best about how the region changes when the orientation is set? So keep that in mind, and hopefully this will make a little bit more sense as we go along. So continuing with that, then we'll also need to figure out how do we want to display the region or expose the region length and the region width. So as I mentioned to begin with, we'll kind of let this evolve a little bit. We're probably going to want to have most of these be private or protected. So let's go ahead and get started here, and we can either do this through the refactoring, or we can do this manually here. So what we can do here is for the integer, for the n, for the number of sides, we can go ahead and create the getter. Likewise, for the region length and the region width, there's probably no harm in doing that. And as well as the orientation, We can essentially make these read only for right now, but what we're going to do is we're going to leave these alone for just a second. We're actually going to manually create some of these. But let's go ahead and refactor these, and then let's go ahead and sneak in then and think about how we want to change some of these, particularly the set orientation. So we're going to add one more. In this case, what we're going to do is we're going to make this a protected setter. So this is going to be protected void set orientation. And what we want to do is we simply want to pass the orientation to it. Now the orientation we haven't defined very well right now, but essentially it's going to be nothing more than a theta. And in this case then our this dot orientation will simply be equal to the orientation. So whatever is passed there, we should do some error checking. So assumed to be a theta in radians, and should do some error checking. All right, continuing on then, what we want to do is we want to think about what the region should look like. Well, right now we have our get for our region length and our region width, but we don't have individual setters. And rather than have individual setters, we would ultimately like to change the entire region in one function. So in this case, what we're going to do is opt, instead of having individual setters, we're going to take an approach similar to the orientation. And in this case, we're going to have a protected void set region. And this set region will accept two input arguments. One is going to be the region length, and the other will be the region width. And at this point, what this will do is this will simply set the region length from whatever value is passed. Once again, you would definitely want to do some error checking here. We're going to take just a second to think about this. So our region width. And so a good example of some validation and a great place to reuse some code would be to have basic validation like the length and width greater than 0. We may also consider a max size, those types of things. So we're going to leave that for a later video. For right now, what we're going to do is just focus on the structure. So at this point, then, we've got majority of our base class set up. The only thing that we want to consider doing here is having a constructor then that we can decide if it will need to be implemented in subclasses. So for instance, what we can do here is we can go ahead and create a Shape2D constructor, and we'll see how this works in just a second. But basically what we would do is we would have a constructor that would then need to be overridden in the subclasses, because once again, our goal is that our Shape2D cannot have its own implementation. So, or rather its own instances. So we'll start off with a public Shape2D constructor, and it's going to accept some of the basic arguments, and that is the region length, the region width, both of which are doubles, and then an int n, which will help us identify the shape that is going to be stored in our Shape2D class. So in this case, what we want to do is, once again, some basic validation, which we'll leave to later. we'll assign the region width. The N. And then the orientation, since it was not provided, we are simply going to initialize to 0. Now, you'll note here that when we see if we can figure out where the error is real quick. 1 second. Aha, okay, so once again, NetBeans is getting out ahead of us here. It's actually telling us that we need our constructor. So if anything, we've probably created a little bit more work for us almost immediately. So I was going to go ahead and demonstrate that you can't actually create an instance of this class, and we'll do that in just a second, but I'm going to go ahead and have to either comment out my subclasses here, or what we'll have to do is we'll have to go ahead and flush these out. So anything that inherits directly from our Shape2D will have to have a constructor. And then also note that as you get further, you're going to essentially push the problem further down in each one of the subclasses. So let's go ahead and start by commenting this out just temporarily. And what we want to do now is we want to come over to our main, and we'll ultimately create some additional functions here. But what I'd like to do is I'd like to attempt to create a Shape2D object. So we're going to say EE333 Shape2D. And so we're just going to call this one example 01. And I'm going to say new EE333 dot Shape2D. And you'll notice here, let's see here. You'll notice here, well, it was there for just a second. There we go. And you'll see here that it is a public abstract class. And so if we try to create a new object of this class, see if we can get our error up here. It actually tells us that it cannot be instantiated. In other words, you can't initialize, declare an initialize, or construct an object of this class. So this will not work. And hopefully now you start to understand this. All right. So real quick, what we want to do is we want to go back and let's go ahead and uncomment this. And what we want to do now is we want to see if we can't get this to a basic point of functionality. So we're going to focus on clearing up some of these errors, and you're going to see that it's going to have a little bit of a cascading effect here on us. But the way we can do this is we can start by creating our constructors for our Ellipse class. So our Ellipse class is going to require at least 2 pieces of information: a major axis and a minor axis. And what we're going to do is we're simply going to make a call to our superclass, and we're going to assume that our ellipse is, at least initially, oriented at theta equal to 0, which means that our major axes will essentially be our length, and our minor axes will be our width. And so the other thing that we want to go ahead and do is we want to go ahead and provide the number of sides. And as I said earlier, the sides for an ellipse will be equal to 0, and that's just how we're going to define it. Another option might be -1, since we don't have the concept of an infinity. So in this case, n equals to 0, and this is the number of sides. All right, now in addition to this, you probably ought to consider having private variables here to be able to store then the information about the ellipse. So for instance, in this case, this is going to be the major axes, private double the minor axes. And at this point, then you can decide then what type of getters and setters you might want for your ellipse. Once again, I would encourage you to not necessarily have any setters here so that you can't necessarily change one of your dimensions directly, but rather that you could maybe have a set size or scale size method and so on. But at this point, then what you would want to do is we simply say this dot major axes is equal to major axes, and this dot minor axes is equal to minor axes. So hopefully at this point, you're starting to see the cascading nature here, and so that you'll see that we've got a little bit of work ahead of us. We now need to think about the constructor for the circle and how it's going to interact with its superclass. And specifically, if you think about it this way, a circle with a diameter is essentially going to be an ellipse where the major and minor axes are the same. So what we can do is we can leverage our circle constructor, or rather leverage the ellipse constructor from the circle constructor. And so what we'll do is here we'll have our public circle. And at this point, it's just going to be the diameter. And then what we will want to do here is we will make a call to our parent class. In this case, we're going to pass to it two diameters, one for the major, one for the minor axes. The ellipse will then handle passing the 0 sides to its superclass and so on. And then you can decide, for instance, how you want to store these values locally. So one of the things that you can consider doing here then is we could say this dot, and you'll notice that we do not have access directly to the major axes and the minor axes. Those are private to the ellipse class. So we've got a couple of options here. So what we can do here is we could create another private variable that is specific to the circle class. So in other words, we could come along here and we could say private diameter. But then if you think about it, the circle subclass essentially has a diameter, a major axis, and a minor axis, even though it can't get access to those private variables. So that's one option. Another option is that we make it appear as if it has a diameter private field by essentially having a getter and a setter, particularly a setter. So you would have a set diameter, and the set diameter would simply then call a function associated with the ellipse. So for instance, we might have a set axes function. And if we had a set axes function, that would set both the major and the minor. And so what we'll do here is we're going to come back to this later on, but hopefully you can start to see the dilemma of how we are going to construct some of our subclasses and where we're going to put the additional fields. We can continue now with the other subclasses, and what we'll do is we'll go through these one by one. With our irregular polygon, the question is, do we want to add any additional fields or methods? And the answer is, for right now, we don't. The only thing that we do want to do is we want to go ahead and create a constructor here for it. And that constructor then will simply take 3 input arguments: the region length, the double of our region width, and then a integer for the number of sides. And at this point, then the only thing we want it to do is simply make a call to our superclass, passing the constructor rather for our superclass, passing the length, the region width, and the end. Now, once again, the assumption here is that we're going to go back and then improve on this as we go along. Right now, all we're trying to do is identify the region that would otherwise surround the irregular polygon. So that's basically the minimum amount of information that we can provide to our constructor at this point. We'll once again improve on this. The other constructors that we would have would provide more information. We're just focusing right now on our structure of our hierarchy. So at this point then, we would want to do the same thing now for our regular polygon, and then the question becomes, what does a regular polygon need? Well, the answer is, once again, those very basic properties: the region length, the region width, and the number of sides. And once again, then the idea here is that we would simply make a call to our superclass constructor, passing not only the region length, but the region width and the end. Now, hopefully you're starting to see a pattern here in this setup. So what we're going to do now is we're going to focus on some concrete classes here. In other words, ones that we actually do intend on implementing some additional functionality in, and that can actually have instances of the class created. Or in other words, there can be actually a rectangle object. With a rectangle, then some of the defining features of a rectangle, of course, would be the side length. And the only reason I'm calling it side length is I want to differentiate that as being separate from the region length, and likewise the side width. At that point then, what we want to do is we want to provide a constructor then would give us enough information about the rectangle to go ahead and create one. And for instance, the double of the side length would be, or double rather, side length as a double would be a reasonable value to pass. A double for the side width, and there would be no need to specify the number of sides or the number of edges with a rectangle. In this case, we know that that would be 4. So when we make a call utilizing our the constructor for our superclass, then what we would do is we would pass the side length, and we would assume that that would be the region length, and we pass the side width as the region width, and then we simply pass then the number of sides. Now, the assumption here, and what I'm intentionally avoiding in this series of constructors, is the orientation. So in this case, once again, this assumes a theta equal to 0 orientation. So basically, you've created a region around a rectangle that is oriented at theta equal to 0. Likewise, now with the square, we can go ahead and create our constructor for the square. In this case, what we'll do here is we'll say public square, and for a square, then we actually only need a single side. And so what we're going to do is we're going to call this one side length. And at this point, then this constructor can call its superclass constructor. So in this case, super, and what we'll pass here will be the side length twice. And remember that in the rectangle constructor is where we pick up the number of sides. So that part is handled. We can also start considering some additional properties to set. For instance, if we go back to our rectangle, you'll notice here that in our constructor, if we do this dot, you'll see that we only have access to the side length and the side width. So we probably want to go ahead, at least to start with, go ahead and assign those properties. Remember that the values for the side length and side width match only when to the region length and region width only when the orientation is equal to 0. But this would then allow for us to be able to set those. And once again, if you come down here to the square, you'll notice that since the fields for the side length and side width are private, the subclass can't see them and then by default then can't edit them. So we'll come back to that part of it in a later video. What I'd like to do now is I'd like to focus on one additional aspect of this. I'm going to go ahead, as I mentioned earlier, we're not going to focus on the triangle right now. We're going to go ahead and comment these out temporarily. We will come back to these then in a later video. Basically with the triangles, the equations just get a little harder. Other than that, the concept is the same. But what I would like to do is then I'd like to go back through some of our classes and see if there are some places that we can do any improvements with respect to our functionality. And namely what I would like to do is I'd like to take one look at the set orientation. So we talked about it up here when we were defining our parent class, the Shape2D, and we have a protected void set orientation, which means that it cannot be seen by any of the subclasses. So for instance, if we come down here to our ellipse and we do this dot, you won't see, you will see the set orientation, the get orientation, but we need to also be able to set the orientation. Now, the orientation for an ellipse, or the way we would set the orientation for the ellipse, would probably be different depending on the geometry. So in other words, how we set the orientation for an ellipse versus how we set the orientation for a square or rectangle might vary based on whether we choose a corner or the centroid. We're going to ignore that temporarily, and we're going to assume that we have some sort of 0 point or an origin point. So essentially what we could do is we could set the orientation for each of our subclasses essentially the same. However, you would agree though that the orientation, or when you change the orientation, you also end up changing the region. So as you rotate the circle, we would not expect to have a change in the region. However, when you rotate a square, you would expect the region to essentially grow and then shrink depending on what theta is. So the idea here is what we want to do is we want to see where do we want to put that behavior. So we started off by having the protected void set orientation. One other option that we could have considered, and I'm going to go ahead and get my code working real quick before we start this. Let's go ahead and check. Yeah, we have no errors. We'll go ahead and Let's go ahead and compile it just to see. Okay, good, everything's fine. So what we'd like to do is we'd like to make a change here. And so instead of having a protected void set orientation, what I'd like to do is I would like to change this now to a abstract function. And we can make this void. We can go ahead and change this to a public. So public abstract or abstract public void. And our set orientation, we're not going to change the name of the function any, but what we're going to do is we're still going to pass the orientation. Remember that that is nothing more than the theta, but now you'll notice that this forces us to implement this elsewhere. So as a matter of fact, we actually have to comment out this particular portion of it. Let's go ahead and comment out all of it here so that we don't get any errors here. And you'll see here now that in our subclass, tell you what, I'm going to take just a second to make this a little easier to switch on and off here. I'm actually going to push this up here. And there we go. All right, so now what you can do is you can simply just comment and uncomment this, sort of understand the behavior here. But now you'll notice that when you have a abstract public void set orientation, it forces you to have the implementation in the subclasses, because essentially the parent class, in this case the Shape2D, can't set the orientation because it doesn't know enough about the subclasses. And the same argument can be made with the set region. But what we'll do here is we're going to focus first on the set orientation, and you'll see now in NetBeans you actually have the ability to implement, in this case, all of the abstract methods in our ellipse, and you'll also get this in the rectangle. And you'll notice here that you got it in the rectangle even though it didn't directly inherit from the Shape2D. It inherited from the regular polygon, which inherited from the irregular polygon, and the irregular polygon inherited from the shape. But since none of these classes are concrete, meaning that they don't have any implementation of the instance implementations, then it had to be implemented in the first concrete class. And in this case, the rectangle was the first concrete class of this hierarchy, which means that both our ellipse and our rectangle are now forced to handle the orientation or setting the orientation. At this point, then, what you can do is you'll notice that we get a default exception thrown if we fail to do this. That's just a template from NetBeans. But what we would like to do now is we'd actually like to make an attempt here to handle this. And what we can do is we can say this, or rather super dot set orientation. And what we'll do is we will make an explicit call to our superclass. However, you'll once again notice that it cannot be accessed directly because it's an abstract method. In other words, the superclass doesn't know how to set the orientation. So what we're going to do at this point is we're just going to go ahead and just simply set then our, we have to figure out then how we're going to get access to the orientation private variable. At this point, you'll notice that the orientation can only be accessed inside of the abstract class Shape2D. So we basically don't have a way, or we have not exposed a way to set the orientation. So for right now, what I'm going to do so that we have a working, functioning model, we're going to go ahead and uncomment the abstract implementation here. and we're going to uncomment this back. So we're going to comment the abstract. And at this point, then what we can do is, at least for right now, we can simply make a call to the parent class's orientation function, which at this point then just assigns the value for the orientation to the private variable. And we can do the same thing now down here in our rectangle. Super.set orientation. So I'm going to stop this project or this portion of the project here. What I would encourage you to do is to go ahead and take a second to implement these classes, as well as take a second to look at the geometry of each one of our shapes that we're trying to handle and identify things that are unique about them. For instance, the way that you would calculate an area or the perimeter. And what we'll do is we'll revisit that in our next video. So hopefully you found this video useful. As always, thank you for watching. If you have any questions, don't hesitate to email me.